Welcome to another podcast. In this episode, we're going to be taking a look at what it means for a function to be differentiable. And I want to start with just a basic description of the derivative once again, since we're new to the derivative. Let's look at the two definitions of the derivative in terms of the limit. Starting with, if I asked you about the derivative, let's say f prime at a point A, the basic definition that we started with is that this is the limit as x approaches A of f of x minus f of a over x minus a. And the other definition, this defines the derivative at a point. So this is the derivative at the point x equal to a. So this is the popular form when trying to find derivatives at a point. If instead I'm after the derivative as a function, the function version of the derivative is usually given by this format, where we take the limit as h goes to 0 of f of x plus h minus f of x divided by h. So this is what we consider the function form of the derivative. Both of these have their uses in different places, and I just wanted to remind you of those and basically ask the question what it means to be differentiable. So what we say here is that the point f of x, or the function f of x, is differentiable at the point x equal to a if and only if there's a couple of properties that come into play here. The property is that the derivative at a exists, which means that this limit definition at the point a exists. So this is based on the limit, in other words, the limit as x goes to a exists. So this is what it means for a function to be differentiable, and anytime we talk about, we talked about continuity earlier in the semester. The idea there was a function could fail to be continuous in a couple of ways. We called that discontinuous, and we looked at those ways. It's the same idea here. We want to look at ways in which a function can fail to be differentiable. So just kind of create a little bit of a list here, and we've got some graphs that we're going to take a look at each of these cases with. But it's three ways a function can fail to be differentiable. So the first thing that's on that list is the function can actually be discontinuous at a point. So rather than keep writing the word function, I'm just going to use f of x to represent the function. We say f of x is discontinuous at, let's just say, the point x equal to a. Then f prime of a does not exist at that point. So the graph that has an example of that is the graph over here on the top right. So this is the graph of the function y equals 1 over x, and you can see that this function is discontinuous at the value x equal to 0. So the function is actually not differentiable at x equal to 0. And this is really easy from a geometric perspective to figure out why that might be the case. Remember, the derivative at a point is the slope of the tangent line at that point. And if you think about what the tangent line at the point 0 for this graph looks like, well, the function's not even defined at that point. So how are you going to write in a tangent line at that point? So this idea of continuity sort of, in some ways, supersedes it. It's a weaker condition than is differentiability. Differentiability is something stronger, that not only does the point have to exist there, but other things have to be in play as well. So just remember, if a function is discontinuous, it can't be differentiable. We're going to have a theorem here in a second to sort of summarize this video, but this is a really good illustration of why that's the case. The second way in which a function can fail to be differentiable is that f of x has a corner. Sometimes people will call this a cusp, but has a corner or a cusp at the point x equal to a. And the reason that this particular criteria makes the derivative fail is that when you have a cusp or a corner at x equal to a, the tangent line is not uniquely defined. And so the example of that is the familiar function, the v shape over here. This is y equals the absolute value of x. This is the absolute value function, and you can clearly see here that at 0, this function has a corner at x equal to 0. Because of that, if I think about trying to draw in tangent lines, because that's just a simple point, drawing in the tangent line and touching at a point is a really easy thing to do, and in fact it's so easy to do there's an infinite number of possibilities. There's all sorts of lines I can draw through just that single point. So at that point, the tangent line actually fails to be uniquely defined. I don't have just one single slope, I have an infinite number of possible slopes. So that's why the function fails to be differentiable at images or pictures that have corners or cusps. A cusp would be something more like this picture. So if we had a graph that does sort of like a wave-like thing, actually that's no longer a function at that point. Remember, to be a function you have to pass the vertical line test. So cusps are sort of these curved on either side, one or both sides. These are what we usually refer to as cusps. And then the corner is where it's straight on both sides. So in either of these two cases, these points at where the cusp or the corner occurs, these are the points at which it fails to be differentiable. The third possible way in which a function can fail to be differentiable is if the function has a vertical tangent. So f of x has a vertical tangent. And this is actually one of the more common ways, other than discontinuity, is that it fails to have a vertical tangent at the point x equal to a. Alright, and so if f of x has a vertical tangent at x equal to a, then the function fails to be differentiable there because the slope is actually undefined. The slope of the tangent line is undefined at that point. And so the limit exists, but it's infinity. And so in that particular case, we say that there is no clear limit at the point x equal to a. So the function has a vertical tangent at that point. And you can see that in this graph that I have up here. This is sort of an odd graph. This is the graph of the cube root of the absolute value function times the absolute value of x divided by x. It's sort of a weird function here, but we can see at the point x equal to 0 that if we were to draw in a tangent line at that point, then the tangent line would definitely have a slope of infinity corresponding with the axis there. And so the tangent line in this case is vertical. Anytime you have a vertical line of tangency, then the function is not going to be differentiable at that point because it's sort of an overload in some sense. You get values of the derivative, the slopes, all the way up to that point. All of a sudden it just goes off the scale because the slope there is vertical. So those are the three ways in which a function can fail to be differentiable. And one sort of nice, neat way to tie a bow on this is there is a theorem which governs kind of what we've been saying here, especially when it deals with continuity. And it's probably worth your time to memorize this theorem. It's very simply stated. If the function f of x is differentiable at the point x equal to a, then f of x is continuous at x equal to a. One way to think about this is if I had sort of a set that represented all possible continuous functions. So this is the set of all continuous functions. Then differentiable functions is a smaller set. It fits entirely inside this one. So these are our differentiable functions. So every differentiable function is continuous, but not every continuous function is differentiable. For example, that function right there, it's continuous, but it's not differentiable. So you can have continuity without differentiability. For example, here we didn't have differentiability at the point x equal to 0, but this function is actually continuous at x equal to 0. So you can lose differentiability at a corner but maintain continuity. So every differentiable function is continuous, but the opposite of that's not necessarily true. Alright, this was just a brief introduction as to what it means for a function to be differentiable and how that can actually fail to occur for a given function. Alright, thank you for watching.